Good afternoon. The first goal of the lecture of today is to show how a rigid motion affects the curvature and the torsion of a curve. In order to do this, I need to introduce some terminology. So last time we proved that if F is a rigid motion over n, then F can be written as the composition of a translation and the linear map associated with an orthogonal matrix. So where Q is in Rn and A is in On. And we also proved that Q and A are unique. Let's introduce the notion of proper and improper rigid motion. So we have definition 1.60. The rigid motion F equal PQ composed with LA is said to be proper if the determinant of the matrix A is 1 and it is said to be improper if the determinant of A is negative 1. The result I want to prove is the following. It's a proposition (1.64), which says that for a regular curve, the curvature let's say the following functions are invariant under rigid motions. These functions are, sorry, I forgot to write proper. This is important. 1. The curvature of a curve in Rn. 2. The torsion of a space curve. So this means we are working in R3, and the third function, which is invariant, is the sine curvature of a plane curve. So this is the R2 case, so n equal to 2. In order to prove this result, I need one lemma. Lemma 1.63, which says let A be a matrix in On, then the orientation of an ordered orthonormal basis V1, V2, Vn over n where it is positively or negatively oriented, agrees with that of AV1, AV2, AV3, AVN, if and only if the determinant of A is equal to 1. Okay, let's prove now the proposition 1.64. Before going through the proof, I would like to explain better the statement. Essentially, it says that if gamma is a regular curve in Rn, is a regular curve, and if f from Rn into Rn is a rigid motion, the image by the rigid motion of gamma hat given by f composed with gamma defined on I with value in Rn is a new curve, and the proposition 1.64 says that if k hat is the curvature of gamma hat and k is the curvature of gamma, then k hat is equal to k. If n is equal to 3, tau hat and tau are respectively the torsion functions of gamma hat and gamma. Then you have tau hat equal tau if the rigid motion is proper. We will prove also that tau hat is minus tau if f is improper. And the last statement is the following: if k at s, k s are the sine curvature functions, then k hat s is ks if f is proper, and we will prove also that k at s is minus ks if f is improper. Okay, let's see the proof of this result. Okay, by proposition 1.58 we know that we know that f is given by TQ compose LA. So if gamma hat is f composed with gamma, then we have that gamma hat t is a multiplied gamma t plus q, where of course q is in Rn and a is in On. Okay, we will denote by v hat and A hat, velocity and acceleration vector of gamma hat. So the first thing to do is what is the relation between V hat, A hat, V and A, that is velocity and acceleration vector of gamma. Let's start by V hat of t. By definition, V hat of t is a ddt of gamma at t, that is a ddt of this function here. We have a gamma t plus q, and this is equal to a ddt gamma t. Why? Because q is a constant and a is a constant matrix. If you want to prove that ddt of a gamma t is equal to a ddt gamma t, what you have to do is to multiply a by gamma t and to compute the derivative of each component, and then you will have to compare this result with the one you get multiplying a by ddt gamma t. Okay, so we got a ddt gamma t, but this is v, so this is a v of t. So we proved that v hat of t is a multiplied by v of t. What about acceleration? So a hat of t this is the derivative of v hat of t, but v hat of t is given by a vt, so I write ddt of a v of t. Once again, I have a product of a constant matrix and a vector, and I want to compute the derivative of this product. So since A is constant, as a constant matrix, I get A ddt vdt, that is A times A of t. So we proved that A hat of t is A times A of t. Now let's observe one fact. This formula implies that the length of v hat of t coincide with the length of a v of t, but A is an orthogonal matrix, so the length of this vector coincides with the length of v of t. So if the curve is parameterized by arc length, then this is equal to 1, and also v hat will be equal to 1. So let's assume that gamma is parameterized by arc length this way we can use this fact and we can simplify the computations. What is now the curvature of gamma hat is k hat, and since we are assuming that gamma is parameterized by arc length, here we prove that also gamma hat is. So this means that the formula for the curvature of gamma hat reduces to this one. K hat is just the length of the acceleration vector. This is true only because of this fact. Gamma hat is parameterized by arc length. But this vector is here. So I have A multiplied by small a. A is orthogonal, so the length of this vector coincides with the length of A. And this is nothing but then the length, the curvature of gamma. So we prove that k hat equal k for any rigid motion. Now, what about the torsion of a space curve? Okay, so in order to prove the statement about the torsion of a space curve, we have to compute the relation between the unit tangent vector of gamma and the unit tangent vector of gamma. So by definition, the unit tangent vector of gamma hat is v hat divided by the length of v hat. We proved before that v hat is AV. It's been proved before. So I can write AV divided by the length of AV. But the length of AB by the orthogonality of A coincide with the length of V. So I can write this as A times V over length of V, and this is equal to A times T. Now we do the same thing with the unit normal vector. So at every time when k is different from 0, we have that n hat by definition is t hat prime over the length of t hat prime, but t hat is here, is equal to at, so I have at prime divided by the length of a t prime. This is the product of, the derivative of a product of a constant matrix and a vector. So you get again a t prime divided by the length of a t prime. By the orthogonality of the matrix A, the denominator reduces to length of t prime. So we get A multiplied by t prime over length of t prime. This is n, the unit normal vector of gamma, so we get a n. So in conclusion, we proved t hat equal a t and n hat equal a n. This is what we proved so far. Okay, from now on we assume n equal 3, so we work with a space curve and observe that T n p, where b is t times n, is positively oriented orthonormal basis of R3. What about this basis here? AT, AN, and AB. First of all, we observe that this is equal to T hat, is written here. AT is equal to T hat. AN is equal to N hat, so I can write N hat A B. So this by lemma 1.63 by lemma 1.63, it is positively oriented if and only if determinant of A equal 1. So this means that F is a proper rigid motion. So let's compare now this basis with this one, T hat, N hat, B hat, where B hat is a T hat times N hat. This is once again positively oriented because the third vector is the cross product of the first two, so is positively oriented, always. So what is the conclusion? What is the relation between these bases and this one? The first two vectors are the same, and this one makes the basis always positively oriented. Instead, this one is positively oriented only if determinant of A is equal to 1. The conclusion is P hat is AB up to a sign. The sign will be the plus if the determinant of A is equal to 1, and will be negative if the determinant is equal to negative 1. Okay. Now, what about the torsion? In order to compute the torsion, we need to make this computation. We need to compute B hat prime comma n. This is plus or minus a b prime comma n. That is sorry, I made a mistake. This is n hat because we want to compute the torsion of gamma hat. So this is plus or minus a b prime multiplied by a n. We proved before that n hat is a n, and this can be written as plus or minus b prime n. Why? Because orthogonal matrices preserve inner products. Okay, so you know the formula of torsion. This is exactly the numerator of that formula up to a sign. So this implies that tau hat coincide with tau if the sign here is plus, which means the determinant of A equal to 1. And tau hat equal minus tau if determinant of A equal negative 1. So in other terms, tau hat is equal to tau if the rigid motion is proper, and tau hat is a minus tau if the rigid motion is improper. And now we have to prove the statement concerning the sine curvature function. So from now on we assume n equal to 2, and let's observe that V R90 V is a positively oriented orthonormal basis What about now this basis here? AV, A, R90, V. Or in other terms, V hat, A, R90, V. According to the lemma 1.63, this is positively oriented if and only if the determinant of A is equal to 1. Remember that A is an orthogonal matrix. Now let's compare this basis with this one, V at R90 V at. This is always positively oriented, and by this statement we get that what is the relation between this vector and this vector here. So this one is positively oriented. So this implies that R90 V at is equal to A R90 V if the determinant of A is 1, and we have to put a minus sign in case the determinant of A is equal to -1. Okay, now we are ready to compare the sign curvature functions of gamma hat and gamma. What is K hat S? This is A hat, comma R90 V hat, but A hat is AV. Sorry, it is A, capital A, and R90 V hat is here. So plus or minus A R90 V. This can be written as plus or minus A, comma, A R90 V, and using the fact that orthogonal matrices preserve inner products, this is plus or minus A R90 V, and this function is nothing but Ks. So this is plus or minus Ks. So we prove that K at S is Ks if the determinant of A is 1, and K at S is equal to minus Ks if the determinant of A is minus 1. In other terms, the sign curvature is invariant if the rigid motion is proper. Instead, the sign curvature changes sign if the rigid motion is improper. And this is the end of the proof. Okay, the next goal of the lecture of today is to prove one of the two fundamental theorems of plane space curves. So theorem 1.65, fundamental theorems of plane and space curves. The first fundamental theorem is about plane curves and essentially says that the sine curvature function uniquely determine a curve up to a proper rigid motion. Instead, the second fundamental theorem is about space curves and says that the curvature function and the torsion function uniquely determine a space curve up to a rigid motion, up to a proper rigid motion. In the textbook, you have the proof of the first one, the one about plane curves. Instead, I will not give the proof of the first one, I will prove the second one. Which is contained in another textbook. It's the famous book by Docalm, Differential, Geometry of Curves and Surfaces, second edition. Precisely you have to look at page 315. Page 315. Okay, let's state these two theorems. So the first one says if I containing R is an interval, and Ks from I to R is a smooth function, then there exists a unit speed plane curve gamma whose sine curvature equals Ks. So this is the first part of the theorem, which is about the existence of a unit speed plane curve whose sign curvature is exactly this function here. Second part, if gamma hat are two such curves, that is two unit speed plane curves whose sign curvature is Ks, then there exists a proper rigid motion F over 2 such that gamma hat is F composed with gamma. So essentially we can say that we have a uniqueness result up to a proper rigid motion. So this is the fundamental theorem for plane curve that I don't prove. The proof is in the textbook. What I will do is to prove the second one, which is the theorem about space curves, and which says the following. So if k tau is a pair of functions, of smooth functions, with k positive, then there exists a unit speed curve, space curve, space curve gamma, whose curvature equals k, and whose torsion equals tau. So this theorem says that if you have a smooth positive function k and a smooth function tau, then there exists a unit speed space curve whose curvature and torsion functions are exactly k and tau. What about the uniqueness? Exactly as before, the uniqueness is up to a proper rigid motion. So if gamma hat gamma are two such curves, then there exists a proper rigid motion f over 3 such that gamma hat is f composed with gamma. Okay, as announced before, I will prove this theorem here. Okay, so we observe the following fact. We observe that the Frenet equations d t dt equal kn dn dt equal minus kt plus tau b and db dt equal minus tau n. Before continuing, please observe that in the Doccarmo textbook there is a different convention for the sign of the torsion. So when you will read the textbook by Doccarmo, you will see that the second equation does not look the same, because instead of plus tau b, it is written minus tau b, and in the third equation, instead of minus tau n, you will find plus tau n. So essentially, if you want to study the proof from this textbook, you have to change the sign of the torsion everywhere. Okay, that said, let's continue. So I was saying that this system of equations may be seen as a linear, let's say, is a system of linear ordinary differential equation which looks like the following: dc1 dt equal f1 of t c1 c9 dc2 dt equal f2 t c1 c9, and the last equation is d c9 dt equal f9 of T C1 C9, where T belongs to some interval I. What are C1, C2, C3, C9? Where C1, C2, C3 are the component functions of T, C4, C5, C6 are the component functions of N, and C7, C8, C9 are the component functions of B. And Fi are linear. Okay, so we are going to use a theorem which says the following. Theorem: given initial condition C1 0, C2 0, C3 0, and so on until C9 0, and S0 in I, and T0 in I, there exists an open interval J contained in I, where I is this interval here. Now, unfortunately, I have to erase. Containing T0 and a unique mapping, a unique smooth actually I should write okay, differentiable mapping denoted by alpha, defined on J with values in R9, such that alpha at T0 is exactly C1 0, C9 0, and alpha prime of T is F1, F2, F9. where each fi I equal 1 to 9 is calculated at t alpha t in j times R9. So what is the meaning of this theorem? It says that the system of linear ordinary differential equations I raised, which can be written as under this form, admits a unique differentiable solution once you fix the initial condition, which is this one. Okay, so we want to apply this theorem to the Fourier equations. Okay, so we can say that as a consequence of this theorem, we have the following fact. Given an orthonormal positively oriented basis, T0 and 0 B0 in R3 and T0 in I, there exists a solution to the Fourier equations. So I can write a family of bases T of t, N of t, P of t, with t in I. I would like to add something. Here I wrote that alpha is fine on J, but it's possible to prove that since the system is linear, the linearity implies J equal I. This is why here I can write t in I. So equivalently, this alpha here is a function defined on I. Okay, so I was saying that if I fix this initial condition, there exists a solution which I write down in this form. So I think of it as a family of bases depending on this parameter. And this family of bases satisfies the following initial condition, such that such that t0 is equal to t0 and t0 is equal to n0 and t0 is equal to b0. This means that the solution at t equal to t0 is equal to this basis here. Okay, the first goal is to prove that this basis here is orthonormal. So far we know only that this one is orthonormal. We want to prove that also this one is orthonormal for any t. For any t in I. Okay, in order to prove this, we have to use a trick. And we consider the functions Tn, Tb, Nb, Tt, Nn, and Bb. And it's possible to prove that ddt of Tn is Knn minus k Tt plus tau Tb. How to prove this formula? First of all, you differentiate the left hand side and you get T prime n plus Tn prime, and then you use the Frenet equations for getting a formula for T prime and a formula for n prime. You will replace those formulas into this expression and you will get this one. It's not finished, we have other equations. We have also ddt of T b equal k n b minus tau Tn, ddt of n b equal minus k Tb plus tau Bb minus tau Nn, ddt of T is twice k Tn, ddt of Nn This is minus 2k nt plus 2 tau nb, and the last equation is ddt of bb equal 2 tau bn. So in total we have 6 equations. Okay, now we want to study this system of equations here. So we want to find a solution. Okay, let's check that a solution, okay, let's say just that the functions Tn equal Tb equal Nb identical equal to 0. Unfortunately I have to erase. And Tt equal Nn equal Bd, this is equal to 1, is a solution of this system with initial conditions zero, 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 one, one, one. What does it mean? It means that if you replace these 6 functions into this system, you get that all the equations which form the system are satisfied. For example, ddt of tt is 0 because the product of t with itself is 1, so the left hand side of this equation is 0. What about the right hand side? Tn is 0 because of what we wrote here, Tn equal to 0. And you can continue, it's very easy to check that this statement is true. And now I have to erase. And what is the meaning of these 6 formula? It means that T, N, and B have unit length, and T and B are orthogonal to each other. So these combined with the uniqueness, this fact combined with the uniqueness of the solution is unique because you can use a version of the theorem I showed you before for the system involving these 6 functions. Ensures that T and B T is an orthonormal basis for any T in I. Okay, the next step consists in defining a curve whose curvature function and torsion function are exactly k and tau. So let's define the curve alpha by alpha of t equal the integral of t of t dt with t in I. It remains to show that the curvature and the torsion of alpha equal k and tau. Okay, so from the definition, it is clear that alpha prime is equal to t. It is also clear that alpha second is equal to k n. Why? Because alpha second is t prime, and we can use the differential equation to prove that this is kn. So this implies k is the curvature of alpha. What about the torsion? In order to compute the torsion, we will use this formula, tau equal alpha cross alpha second, comma alpha third, divided by the length of alpha cross alpha second squared. Okay. Sorry, this is alpha prime. Okay, then we need alpha third. Alpha third is k n prime, that is k prime n plus k n prime. We made already this computation. If you look at page 46 of the textbook, you will find these details. So this is k prime n plus k minus kt plus tau b, where I'm using the Frenet equations for n prime, for a formula for n prime. So this way you get k prime n minus k square t plus k tau b. Okay, if you now use this formula, you have that the torsion is t cross kn minus k square t plus k prime n, sorry, minus, no, plus, minus k plus k tau b divided by k square. Okay, if you multiply, you will get that t times kn is a vector parallel to b, precisely is kb. Then when you multiply this vector with this, the unique non-zero component is the one you get from here, from the product of t cross kn and k tau b. Precisely you get k square tau over k square equal tau. So this says that tau is the torsion of alpha. So we proved that the curve alpha of t equal to the interval of t of t dt is the curve having k as a curvature function and tau as torsion. What about now the uniqueness? Is this curve unique? The answer is yes, up to a rigid motion. Okay, uniqueness of the curve. Suppose that alpha at is another curve such that k at t is equal to kt. So this means its curvature function coincides with the curvature function of alpha, and tau at t is equal to tau t with t in I. Let's suppose also that t at 0, n at 0, b at 0 is the Frenet frame of alpha at at time t0. Okay, since it is positively oriented, then there exists a rigid motion that send the frame of alpha, this is the frame of alpha, to t at 0 and at 0, b at 0. Also, this one is positively oriented because b0 is t0 cross n0, so this rigid motion is proper. Then apply the uniqueness part of the theorem about systems of differential equations and deduce that let's say t at is f applied to t, ft, n at is equal to f n, and b at is equal to f b. Why this is true? Because t at, n at, b at have this as initial condition, and t and b have this as initial condition, and the relation between these two initial conditions is written here, where f is the rigid motion. In other terms, t at 0 is ft0, n at 0 is fn, and b at 0 is fb. Once you have that t hat, n hat, b hat are related to t and b this way, then you can conclude that alpha at is the integral of t at t dt, that is the integral of f tt dt equal f applied to t of t dt, that is f alpha t. So this proves that alpha and alpha at differ by a rigid motion which is proper. So this is the end of the proof. For today that's all. Thank you for your attention.